Section: Introduction. In this section, we explore autoregressive models, which are effective tools for understanding and creating various types of content. By transforming different types of data into discrete forms using specialized tokenizers, we can use a single transformer to handle text, images, audio, and even molecular data. We observe that, similar to large language models, these models show predictable performance improvements as they grow in size and computational power, leading to their increased use in both research and industry. In particular, autoregressive models are being examined as a viable alternative to diffusion models for generating high-quality images. As high-quality generative models become more common, detecting AI-generated content has become more difficult, raising concerns about potential misuse, such as deepfakes and violations of intellectual property. One promising solution is generative AI watermarking, where model providers embed subtle signals in the generated content to verify its source, even after common alterations. Recent studies in this area can be divided into two categories: post hoc methods that modify existing content and generation time methods that adjust the creation process of specific models. The latter is common in watermarking large language models, providing reliable detection with low false positive rates. However, most research on image watermarking has focused on diffusion models, and no one has yet tried to adapt language model watermarks for other types of tokens, which could lead to a strong watermark for autoregressive image generation models. This leads us to our main question: can we effectively watermark autoregressive image generation models at the token level? To address this question, we extend language model watermarks to the tokens generated by autoregressive image models. We identify a significant technical challenge. While the process of tokenizing and detokenizing an image is designed to maintain consistency, the reverse process often fails. We find that when we decode model-generated tokens and then re-tokenize the resulting image, about 1/3 of the tokens change. This issue worsens if the images undergo transformations, like compression or cropping, which is common in practice. Although this reverse cycle consistency, RCC, may not affect model performance, it is essential for effective watermarking. To tackle this, we implement two main strategies. First, we introduce a lightweight fine-tuning process that enhances the consistency of the detokenizer and tokenizer, boosting the watermark's strength and resilience against transformations and attacks. Second, we add a post hoc watermark synchronization layer that helps recover original tokens after geometric changes, such as flips. Our experiments demonstrate that this results in a watermark that maintains quality, is effective, and is robust. Our key contributions include the first study of watermarking for outputs from autoregressive image generation models, adapting language model watermarks to achieve theoretically sound results. We highlight the challenge of reverse cycle consistency and propose a fine-tuning method to improve it, significantly enhancing watermark strength and robustness. Additionally, we introduce a synchronization layer for geometric robustness using localized watermarking. Through extensive experiments, we show that our watermark is strong, preserves quality, and remains effective against various transformations and attacks. In terms of background, we focus on autoregressive image models, which have been a long-standing approach to image generation. This involves learning an image tokenizer and training an autoregressive model, like a transformer, to generate images by producing corresponding token sequences. Notable examples include DAL-E and Party. Our work does not address models that use continuous representations or combine diffusion with autoregressive methods. Section Summary. In this section, we explore the potential of watermarking outputs from autoregressive image generation models by adapting techniques from large language models, LLMs. We identify the challenge of reverse cycle consistency, RCC, in tokenization and propose strategies to enhance watermark robustness against various transformations, ultimately demonstrating a strong and quality-preserving watermarking approach. Section: Tokenization. In this section, we discuss tokenization, which involves mapping data samples, like text or images, to sequences of integer tokens using a predefined vocabulary. The process can be reversed by a detokenizer. Most text tokenizers use byte pair encoding, while image tokenization mainly relies on vector quantization. We typically use VQVAE and its variants, which consist of an encoder that transforms data into soft latents, followed by a quantizer that assigns discrete tokens based on the nearest codebook entry. The detokenizer then converts these tokens back into hard latents and uses a decoder to recreate the original sample. All components are usually trained together with a focus on reconstruction. Next, we explore watermarking AI-generated outputs, which can be categorized based on when the watermark is applied. Generation time watermarks modify the output during creation to embed detectable patterns, while post-hoc watermarks adjust already generated outputs. We define a watermarking scheme as 0-bit if it only indicates the presence of a watermark, and multi-bit if it conveys a binary message. Post-hoc methods are versatile, but generation time methods that change content often provide better resistance to attacks and more reliable detection. We focus on the LLM watermarking method that uses a secret key and previous tokens to randomly divide the vocabulary into green and red tokens. The strength of the watermark is applied to the green tokens, and a detector counts these tokens to assess the presence of a watermark. A low p-value indicates that the content was generated with the watermark. For watermarking autoregressive image generation, we tackle the challenge of low reverse cycle consistency through tokenization, fine-tuning, and watermark synchronization. Our experiments show that this approach results in a strong watermark without compromising generation quality. In our setup, a model provider, whom we refer to as Alice, deploys an autoregressive model capable of generating mixed text and images. We assume she uses byte pair encoding for text and vector quantization for images. Alice aims to implement a 0-bit watermark that can be detected later, without altering the model's weights. We also assume that Bob only has black box access to the model and cannot access the tokenizer or detokenizer. Section Summary. In this section, we discuss the tokenization process for various modalities, primarily focusing on text and images, where tokenizers convert data samples into integer tokens using predefined vocabularies, and we explore watermarking techniques for AI-generated outputs, distinguishing between generation time and post-hoc methods. We also present our approach to watermarking autoregressive image models, addressing challenges related to reverse cycle consistency to ensure robust watermarking without compromising generation quality. Section: Adapting LLM watermarking. In this section, we adapt watermarking for large language models, LLMs. When we generate text, we apply the KGW method directly. For images, we use a fixed split that is known to make watermarks less secure for text, but it may work better for us due to the nature of VQ tokenizers. We explore both approaches in our experiments. We also have the option to choose the watermark context. However, we found that using the structure of images did not improve our results, even though we thought that using tokens from nearby regions might enhance robustness. We discuss this and other watermark parameters in the appendix. For detection, if Alice suspects that certain samples were generated by our model, she can apply a unified scoring method. We first tokenize each sample to a specific length and score it accordingly. We then sum the scores and remove duplicates to maintain statistical integrity. Finally, we calculate a single p-value. If this p-value is below a certain threshold, Alice can flag the content as watermarked. We investigate the advantages of watermarking multiple modalities together and discuss the trade-offs involved. In our visualizations, we show how the watermark is applied to images generated with taming, specifically on the latter half of the tokens. Our experiments confirm that the watermark subtly alters images while maintaining a high level of confidence in its presence. We also address the challenge of reverse cycle consistency, RCC. The tokens we use for detection are generated by the autoregressive model, which may not reflect reality. To apply the detector, Alice must first tokenize the sample. If the tokens differ significantly, the watermark could be lost. We define a token match to quantify this, stating that RCC holds if the match is above a certain threshold. Interestingly, RCC is not guaranteed even in text, despite certain tokenizers ensuring forward cycle consistency. For instance, if certain tokens exist in the vocabulary, they may be re-tokenized into a single token, violating RCC. We provide a real example of this in the appendix. However, RCC generally holds in practice, as evidenced by our experiments showing a high average token match across multiple completions. We also repeat our experiments with image models and present the results. We consider cases where images undergo transformations before re-tokenization. Without transformations, RCC is weaker than expected. Our findings indicate that common transformations like blur or JPEG compression significantly lower the token match, while geometric transformations further reduce it. This behavior can be explained by the fact that neural image tokenizers are trained for forward cycle consistency, and their training data does not include detokenized samples. Additionally, the tokenizer's sensitivity to spatial changes means that even minor edits can alter most tokens. We will discuss strategies to mitigate these issues. Section Summary. In this section, we explore the adaptation of watermarking techniques for both text and images generated by LLMs, examining the effectiveness of different watermark contexts and the challenges posed by reverse cycle consistency, RCC, in maintaining watermark integrity across modalities. We find that while watermarking can be effective, transformations applied to images significantly impact token matching, necessitating strategies to mitigate these effects. Section: Fine-tuning for reverse cycle consistency. In this section, we propose a fine-tuning procedure to enhance reverse cycle consistency, RCC, in image tokenizers. We recall the components of our vector quantization, VQ, system, which includes the encoder, quantizer with a codebook, and decoder. To avoid the expensive retraining of the quantizer, we keep its weights fixed. Instead, we focus on fine-tuning the decoder and a replica of the encoder, which we use solely for watermark detection. Our goal is to optimize RCC by training the decoder so that its outputs can be reliably inverted by the encoder replica. For our fine-tuning objectives, we first pre-compute tokenizations from a set of images to use as training data. We encourage RCC by minimizing a loss that matches the original hard latents to the soft latents obtained after detokenization and encoding. To ensure robustness under transformations, we apply random augmentations during training, which include brightness adjustments, contrast changes, and weak geometric transformations like rotation. We gradually increase the strength of these augmentations throughout the training process. To maintain the quality of the decoder, we introduce a regularization term that keeps its performance close to its initial state. We found this approach to be effective and easier to train than other methods. We jointly train the decoder and encoder replica to minimize a combined loss, which we demonstrate improves RCC and watermark robustness against various attacks. Next, we address the challenge of recovering watermarks after geometric transformations, which can alter image tokenization. Instead of running the watermark detector on multiple transformed copies, we repurpose localized watermarks as synchronization signals. We embed a fixed set of messages that help us estimate the applied transformation, allowing us to revert it before using the original watermark detector. This ensures that our watermark remains robust and does not degrade performance. In our implementation, we embed synchronization messages into the four quadrants of the image. We find that the original watermark is preserved even after adding this signal. However, transformations like horizontal flips can disrupt detection. To counter this, we use an algorithm that searches for the best alignment of the messages, enabling us to identify and revert flips, rotations, and crops. We note that our synchronization pattern assumes certain cropping conditions, but the concept can be adapted for more complex scenarios. Our procedure effectively detects transformations and restores the watermark. We will provide further details and examples in the appendix. Overall, we show that synchronization enhances geometric robustness, complementing our RCC fine-tuning efforts. Section Summary. In this section, we propose a fine-tuning procedure to enhance reverse cycle consistency, RCC, in image tokenizers by optimizing a decoder and an encoder replica while keeping the original encoder fixed. We also introduce a synchronization method using localized watermarks to recover watermarks after geometric transformations, ensuring robustness against various attacks while maintaining the integrity of the original watermark detection. Section: Experimental Evaluation. In this section, we evaluate our experiments. We measure how RCC fine-tuning and the synchronization layer affect RCC, watermark quality, and power. We also study robustness against common transformations and attacks, as well as joint watermarking of text and images. More details and results can be found in the appendices. For our setup, we use 3 autoregressive image generation models. The first is the class conditional ImageNet transformer, which generates images at a resolution of 130 by 130 using a VQGAN tokenizer. The second model is the 133B variant of Chameleon, capable of generating interleaved text and images. Lastly, we use RAR-XL, a state-of-the-art model that generates 130 by 130 images based on ImageNet classes. In each experiment, we generate 4 samples per model, totaling 56 samples across 14 ImageNet classes for the first 2 models and 4 COCO prompts for Chameleon. We evaluate several variants of our method: base, which uses the original models, featuring an FT plus OGS, which apply the same watermark after RCC fine-tuning, with and without training augmentations, and FT plus OGS plus sync, which includes our watermark synchronization on top of augmented RCC fine-tuning. We fine-tune models on tokens from ImageNet training samples for 14 epochs, using different hardware setups for each model. We focus on whether our fine-tuning procedure can improve reverse cycle consistency, RCC, in image tokenizers and enhance watermark power. We present results using taming and repeat similar experiments with Chameleon and RAR-XL, reaching comparable conclusions. Our findings show that fine-tuning improves RCC. We generate class-conditioned ImageNet samples and measure token match between generated tokens and those from re-tokenized images. Our results indicate that fine-tuned variants consistently achieve better token match scores, demonstrating the effectiveness of fine-tuning in enhancing RCC. While augmentations and synchronization slightly reduce token match on unmodified images, they significantly boost robustness. We also find that fine-tuning enhances watermark power. The true positive rate of the watermark detector improves across all variants, especially at lower false positive rates, indicating that RCC gains translate into better watermark performance. Importantly, watermarking and fine-tuning do not compromise generation quality. We compute the Frechet inception distance, FID, for generated samples and find that none of the variants exceed the FID of the unwatermarked base model, confirming that our watermark maintains generation quality. The FID for FT plus OGS plus sync shows a minor increase due to the synchronization watermark. We provide qualitative samples for all models in the appendices. Section Summary. In this section, we evaluate the impact of our proposed fine-tuning and synchronization methods on reverse cycle consistency, watermark power, and generation quality across 3 autoregressive image generation models. Our results show that fine-tuning improves reverse cycle consistency and watermark power without compromising the quality of generated images, as evidenced by consistent FID scores across different model variants. Section: Watermark Robustness. In this section, we discuss the robustness of our generative model watermark against various transformations and removal attacks. We evaluate the watermark's true positive rate, TPR, at a fixed false positive rate, FPR, across different transformation strengths, using the same setup as in our previous work. We present our findings for 3 models, averaging TPR over various transformation parameters. Our main conclusions are consistent across all models, indicating that our approach is transferable despite differences in model specifics. We find that fine-tuning significantly enhances robustness against volumetric and attack methods. Initially, the watermark is vulnerable to certain transformations when applied to the base model. However, with fine-tuning and augmentation, we see a marked improvement in robustness, particularly against neural compressors and the challenging diffusion purification attack. We note that excessively high values can distort images too much, making them less relevant, a trend observed in RAR XL but less so in Chameleon, which shows inherent robustness. We also address geometric robustness, which remains low across all models, even with fine-tuning. This is expected since autoregressive models struggle to maintain token sequences during semantic changes. To tackle this, we introduce a synchronization layer that helps estimate and correct these changes. Our results show that synchronization greatly enhances geometric robustness while maintaining watermark strength on unaltered images, though it may slightly reduce robustness against moderate-value metric transformations. We compare our method to post-hoc watermarking techniques, which are not specifically designed for autoregressive image generation. While these methods may perform comparably on value metric transformations, they often fail against geometric attacks. Our watermark, grounded in randomness, offers theoretical guarantees and has been empirically validated, unlike post-hoc methods that can introduce bias. Lastly, we explore the joint watermarking of multiple modalities generated by the same model. We find that scoring more equally watermarked tokens improves detection power. However, when acquiring more tokens isn't feasible, joint watermarking across modalities becomes essential for reliable detection. For instance, we simulate a scenario where Alice wants to prove that an online article was generated by her model, using interleaved prompts to produce both text and images while attempting to obscure the watermark through random token changes. Section Summary. In this section, we evaluate the robustness of our generative model watermark against various transformations and removal attacks, finding that fine-tuning significantly enhances resilience to these challenges. We also introduce a synchronization layer that improves geometric robustness while maintaining watermark integrity, and we compare our method favorably against existing post-hoc watermarking techniques, highlighting its unique ability to watermark content through semantic modifications. Section: Benefits of Joint Watermark Detection. In this section, we discuss the advantages of joint watermark detection. The orange line in our figure shows the true positive rate, TPR, at a specific false positive rate, FPR, when only the text is watermarked. We notice that the TPR quickly declines as the text becomes more corrupted. Since we use all suspect text, it becomes challenging for us to enhance detection in this situation. However, when both the text and the image are watermarked using our method, detecting the combined tokens significantly strengthens the watermark's effectiveness. For instance, at a certain level of text corruption, the TPR improves and remains high, even when the text-only detection drops significantly. Additionally, we obtain a reliable p-value, which would be difficult if we watermarked the modalities separately. Our method also shows resilience to moderate image changes, and we see a similar pattern when we introduce Gaussian noise. However, we must consider a trade-off. Adding a weak watermark can hinder detection, as seen when the TPR falls below a certain threshold with strong noise, making text-only detection more favorable. In the next part, we explore whether our approach can be applied to other modalities, specifically through a case study on audio. We investigate autoregressive audio generation using Moshi, a transformer-based speech-text model. We encounter similar challenges and results as with images, but we also identify key differences. We refer to various appendices for detailed discussions and extended results related to audio. Regarding audio tokenization, MOSHI's tokenizer uses a method called residual vector quantization, RVQ, which quantizes the residuals from previous quantizers. Each token represents a short time frame of audio. We also examine the RCC properties of MOSHI's tokenizer, finding that the first stream maintains some cycle consistency, which diminishes in later streams. Our experiments show that transformations worsen this consistency. To adapt our fine-tuning procedure for audio, we modify our approach by using pre-projection soft latents as targets and replacing certain loss functions with multi-resolution STFT loss. We also apply audio-specific augmentations during training. In terms of synchronization, we found that no localized audio embedder was robust enough under time-frequency edits, so our experiments focus on the effects of fine-tuning. Future work could enhance audio-specific localized watermarking for better synchronization. When watermarking multiple streams, we observe that earlier RVQ streams are more consistent and likely to preserve the watermark. However, limiting watermarking to a single stream results in too few tokens for reliable testing, while watermarking all streams introduces noise. We find that watermarking the first 4 streams strikes a good balance. Section Summary. In this section, we demonstrate that joint watermark detection significantly enhances performance, as combining watermarked text and images improves detection rates even under high corruption levels, while also providing rigorous statistical validation. We also explore extending our method to audio, noting similar challenges and proposing adaptations for audio-specific fine-tuning and synchronization, ultimately finding that watermarking the first few streams balances reliability and noise. Section: Experimental Setting. In this section, we perform RCC fine-tuning to achieve FT and FT plus OGs using the Vox Populi dataset, resulting in a final PESQ score of 174 compared to the base samples. For our evaluation, we create 175 watermarked audio samples with Moshi, using 4 text prompts generated by LLAMA 3.1 to 8B instruct, which we then convert to audio with SEAMLESSV2. We set specific parameters and watermark the first 4 audio streams as previously described. In our results, presented in the audio table, we find that watermarking does not significantly degrade audio quality, and we achieve strong watermarking even without RCC fine-tuning. We notice that the base model already has some time-frequency robustness, likely because non-semantic streams are used to carry the watermark. Interestingly, fine-tuning without augmentations reduces time-frequency robustness, but this is restored with FT plus OGs. We believe this decline may be due to catastrophic forgetting, as the model learns to detokenize audio in a way that is not resilient to time-frequency changes. This indicates that augmentations are crucial for effective fine-tuning, aligning with our findings on images. However, while FT plus OGs enhances robustness in value metrics, it does not sufficiently improve time-frequency robustness, leaving this issue for future exploration. Lastly, although we are not aware of audio methods similar to diffusion purification, we assess robustness against neural compression techniques like DAC and encodec. We find results comparable to post-hoc AUDIOSEAL, even though we do not specifically train against encodec during fine-tuning.